Okay, now we're going to do something very similar to what we did on problem 1 on the tear-off, only this time we're going to be getting our information from the function itself rather than the graph of the derivative. So let's see how we do it, and notice how we parallel the same steps that we took in the last example. First of all, we look at the domain of the function. The domain of the original function is all real numbers. There are no problems with cube roots. Cube roots are defined for all x. Okay, does the function have any asymptotes? And the answer is no. Okay, we're looking at the function. And the intercepts, we set f of x equal to 0, which will be when x to the 1/3 times x plus 4 equals 0, so x equals 0, and x equals -4. And that gives us 2 points on our graph, 0, 0, and -4, 0. And then to find the y-intercept, we find the function value at 0, which we know is 0. So it's y equals 0, and the corresponding point is again 0, 0. Critical numbers, how do I find those? I see where f prime of x is equal to 0. That's where the numerator is equal to 0, the numerator of the derivative, and that's at x equals -1. Okay. We also want to consider where f prime of x is undefined. That's where the denominator is equal to 0. That's at x equals 0. Now, is that a critical number? Again, I go back to the domain of the original function. 0 is in the domain. We've already seen that it's an intercept. And so, yes, it would be a critical number. So we have critical numbers at -1 and 0. Horizontal tangent line, that's going to be where f prime of x is equal to 0, and that will be at x equals -1, as we just saw. Vertical tangent line, that's where the derivative is undefined. Going back to our basic correlation, the derivative tells us the slope of the tangent line. If it's vertical, a tangent line has no slope. And so we see that that's going to occur at x equals 0. All right, I can set up my number lines for my two derivatives for f prime. It is where x is -1 and 0, and my derivative is this. If I plug in, it's certainly going to be positive for x greater than 0. It's going to be positive if x is, say, -1/2, because the numerator is positive and the denominator is positive, because we have an even power in that denominator. It'll be the cube root squared, so it's always positive. If x is less than -1, the numerator is negative, but the denominator is positive, so it will be negative. And so our function f is going down, coming back up, and staying up. Okay? So, reading off that number line, I see we have a relative minimum at x equals -1, and a relative maximum. Oh, there is none. That's okay. You don't have to have a max or a min at any point. What's the minimum value? The minimum value is f of -1. I go back to the original function, so that's 3/4 times -1 to the 1/3 times -1 plus 4, which is 3/4 times -1 times 3, so it's -9/4. Which is what? -2 1/4. Okay? And now I want to do the number line for f double prime. Let me go ahead and do it here since I've already used my space. F double prime, okay, is x minus 2 over 3x to the 5/3. And I know that f double prime equals 0. I can look at that. That's going to be where x equals 2. F double prime of x is undefined. And that's at x equals 0. Again, 0 is in the domain of the function, so we can have a possible inflection point or change of concavity at 0. Okay, now I just look at my values. Certainly it'll be positive if x is greater than 2. And if x is 1, numerator's negative, denominator's positive, so the second derivative is negative. If x is less than 0, say at -1, the numerator's negative and so is the denominator. This time it's x to the 5/3, so that would be a negative value. Okay, so negative over negative is positive. Just double check when you're doing these problems, make sure that those signs are right, because you can know exactly what you're doing, but if you have the signs wrong, you're going to miss the problem. All right, so what does that tell us about the function? It's concave up, then down, then up, and it looks like there are actually 2 inflection points because both 0 and 2 are in the domain of the function. So what are my inflection points? If x is 0, we know that y is 0. We've already seen that. If x is 2, we have to figure f of 2. And that is not something that I can find easily without a calculator. But fortunately, we don't need to know that because we were told that that's approximately 5.7. We were given that information initially, so that will be our inflection point. Okay? Basic information about the graph. All right, now what we want to do is take that information and sketch the graph. So let's do that. See if we can put these two together, put the information that we have on our number line, and then connect the dots. Okay, so what do we know? We had 2 intercepts. Going back again, a little awkward here. Let's see, the intercepts were at 0, 0 and -4, 0. We have no asymptotes. So we have our 2 intercepts. Then we had our critical numbers, and those occurred at -1, and we found the function value -1 was -2 1/4. And then we had our inflection point was at 0, 0, and 2, approximately 5.7. 1, 2, 3, 4, 5.7 would be right about here. So those are the points that we know on the graph. And the question is, how do we graph? Well, what I like to do is take our 2 number lines and put them together for the graph of the actual function. Okay, so what do I know? I take the points, okay, -1, 0, and 2 were the significant points. And I put my 2 number lines together. Notice that the function is decreasing and concave up until -1. So decreasing and concave up, that's the shape of the graph. What happens at -1? It's increasing, but it is still concave up all the way to 0. Oh, and there's a min, just like we anticipated. Okay, what happens at 0? Still increasing, but at 0 there's a change of concavity. There's our inflection point. And then what happens at 2? Still increasing, but another change of concavity, so it turns around, the shape changes. Okay, does that make sense? I've just looked at my 2 number lines, combined them into 1 for the function. Okay, now I've done the hard part. Now I get to draw pretty pictures. Okay, so I just connect the dots using these shapes. So it must be doing something like this, going through the intercept. Okay, that intercept was the only reason it's there is that it's an intercept. It's not a significant point. But then we see at -1, we're going to start increasing. So there's our min. And then what happens at 0? Swap of concavity. Be sure to label this as an inflection point because sometimes it's hard to see exactly where that occurs. And then at 2, turns around, change a concavity again, and we get our graph very easily. So the process is finding all of the information carefully from the function and its derivatives, put that together to get the shape of the graph, and then finally connecting all of the dots. Make sure you have the function values. That's why we need to know both x and y values for each of those points. And that's graphing. It's very satisfying when you've got it right, okay? And again, make sure the details are right. If you've done it correctly, you'll know, and I can tell you this from experience, if you've done something wrong, you usually can't draw the picture right. So you can go back and double check, make sure all of your signs are correct, and you've got all the correct information. Thank you.